All right, so here's the electromagnetic spectrum. The electromagnetic spectrum just contains all different types of electromagnetic waves. And here they are arranged in wavelengths, so increasing wavelength, shorter wavelength. And arranged in a funny way like this because see the speed of light, C is frequency times wavelength, and as frequency increases, wavelength decreases, okay? And the energy of a photon is the Planck's constant times the frequency. So the higher the frequency, the greater the energy, okay? So what you see in the spectrum is it's arranged in form of increasing frequency, of increasing energy, and decreasing wavelength. So frequency is increasing, decreasing wavelength. So that's why it's arranged like that. Okay, so here's the electromagnetic spectrum, decreasing wavelength and increasing frequency. And now, here's a fundamental fact. So, so if you want to see an object like this size, so B is the dimension of an object. To see this object, what you need to do is you need to use an electromagnetic wave whose wavelength is smaller than this object. Okay, so the largest wavelength you can use to see this object is roughly the size of that object. And if lambda is greater than the size of the object, you cannot see the object. Okay. So let's go back to that. Okay, so that's what this thing is sort of indicating. Okay, so here are the wavelengths. And a wavelength of 10 minus 10 meters, that's roughly the size of a water molecule. So if you wanted to see a molecule, you would have to use this wavelength or less or shorter. Okay, so you could see a virus with visible light. You could see a cell with visible light. Okay, so you could see this object with any of these radiation, anything on the right with a shorter wavelength. Okay, now you couldn't see this guy with all these guys. Okay, so you couldn't see a virus with a radio wave. Okay, you couldn't see that. All right. And here are the same wavelengths, the electromagnetic spectrum arranged in terms of higher frequencies. So these are gamma rays, X-rays, and so on. Visible light, radar, microwaves. Microwaves have frequency of about 10 to the 10 hertz, and so on. So that's the electromagnetic spectrum. And here's the electromagnetic spectrum again. So arranged in higher frequencies, gamma rays have higher frequencies and higher energies, X-rays, UV light, and so on. And this is the scale. Again, using radio waves, you could see buildings, but you couldn't see anything smaller than that. Okay, and so what this is showing you is that these temperatures, all objects emit electromagnetic radiation, and that would be the predominant power it would emit. Okay, the sensors we are born with, so your eyes, are sensitive to that narrow band of electromagnetic waves. So the visible band is very narrow. Okay, so Kavi, wait. Okay, so the visible band is extremely narrow part of the electromagnetic spectrum. Okay, so there's the visible band, and the wavelengths. So again, the wavelengths are shorter in that end. So the blue end of the spectrum has shorter wavelength. The red end of the spectrum has larger wavelength. Okay, so we can see our eyes are sensitive from roughly from 700, these are in nanometers, 700 to 400 nanometers. Okay. And it turns out, so every wavelength appears a different shade, as you can see. So different wavelengths have different colors. And so we can see from 700 to 400 nanometers, our eyes are most sensitive to 550 nanometers, which is a yellow-green color, so 550 nanometers of roughly yellow-green color. And we can distinguish about 7 million shades. Okay. So, some of you guys might be aware that your computer screens can render about 16 million shades, but anyway. Okay, so now let's talk about microwaves for a second. So this is a water molecule, and you know that the water molecule has a dipole moment, okay? So the oxygen atom is electronegative or greedy for electrons, so the negative charge center is there, and there's the positive charge center. So let's draw. Okay. All right. So here's the water molecule, and okay. So water molecule is a dipole moment like this. Okay. And the dipole moment is denoted by P. Okay, we'll just write it like this. So here's the water molecule represented like that. And now if you put this water molecule in an electric field, so let's say we put it in an electric field like this. What this electric field will do is will turn this dipole moment in that direction. Okay, so the electric field will grab hold of the water molecule and turn it like that. And now, if you switch the electric field back like that, the water molecule that was turned that way, now it's being turned back this way. And now, so if you send an electromagnetic wave like that, as this electromagnetic wave goes through there, the electric field is going back and forth. So if you send an electromagnetic wave in this direction into this water molecule, it will grab hold of a water molecule and jiggle it back and forth. Okay. So the electric field in the electromagnetic wave can grab hold of the water molecule and jiggle it back and forth. Okay. So what it's doing is, here's the water molecule and it's being jiggled back and forth. Okay. And so when you use a microwave, the electric field, the frequency of the microwave is about 10 to the power 10 hertz. Okay, so you're grabbing hold of a water molecule and jiggling it back and forth 10 billion times a second. That's what that means. Okay, so the oscillating electric field in a microwave oven exerts a torque on water molecules because of their dipole moment. And the torque reverses direction 5 times 10 to the 9 times, 5 billion times per second. So the microwave heats the water, and the water molecule, because it's bound to the surrounding molecules, will transmit some of the energy gain, and that's how you heat your food. So interactions between the water molecules distributes the energy being pumped into them. Okay. All right, so here's how you emit radio waves. Here's a dipole antenna. There's the oscillating circuit. You pump energy into this oscillating circuit, which is coupled via transformer there. And this, so essentially what you're doing is you're taking an electron and jiggling it here between these two guys. And this is emitting electromagnetic radiation. Okay. The frequency of the electromagnetic radiation is equal to the frequency of this oscillating circuit, which is LC. So if you want to emit different frequencies, you change the frequency of, you change C or L, and you can emit different frequencies. So this is a dipole antenna. And to radiate most efficiently, the length of this rod, each rod has to be 1/4 the length of the wavelength. Okay. So the length of each rod is equal to 1/4 the wavelength of the emitted radiation. All right, so now what we do is in our wireless communication, we can't depend without wireless communication. So here are some of the bands. Okay, so AM radio uses about 1 megahertz. FM radio uses about 100 megahertz. TV radiates in that channel. Ultra high frequency TV is in that channel. Cell phones use that. Wi-Fi uses those frequencies and so on. Okay. Now we do two modes of communication. This is called amplitude modulation, and this is called frequency modulation. So this is amplitude modulation, this is frequency modulation. So amplitude modulation is what is AM radio uses amplitude modulation. That's what AM means. And FM means frequency modulation. Okay, so what these do is, and again, so this, if you became an electrical engineer, you take signal processing classes and you learn about all of this. Okay, so the carrier frequency is that green frequency. So the carrier signal is that green wave. And the signal is the blue wave. So the signal, the information that you're trying to transmit generally has a low frequency, the carrier signal has a much higher frequency. So you combine, you imprint the information on the carrier signal, and now the carrier signal got modulated, and see the red signal is the result, the modulated signal, and that's being transmitted. Okay, so that's how AM amplitude modulation works. It's just that AM modulation, the advantage of AM modulation is it travels, the signal travels further, lower the frequency, the further it will travel. Higher the frequency, it doesn't travel as far. But the problem with it is you get a lot of noise interference on this signal. With frequency modulation, you're using a higher frequency, and what you're doing is there is the information that you're that's being transmitted. You take a Fourier transform of that, and you vary the frequency of the carrier signal, the green signal, with the frequency of this information signal. Okay. And you're changing the frequency of the carrier signal. So the red signal you see doesn't have constant frequency. So that's frequency modulation. And the advantage is you have practically no interference with frequency modulation. The price you pay is you can't send signals as far. So you can potentially catch AM radio from New York, but you can barely catch FM radio from Orlando yet. So in radio system, frequency modulation is canceling naturally occurring noise. So frequency modulation, there's each AM station is assigned a specific carrier frequency and is allowed to vary by plus or minus 5 kilohertz. In FM radio, the frequency of each station is allowed to use 100 kilohertz on each side for its carrier frequency. So what that means is, so let's, let's say 89.9 megahertz is the public radio signal. Okay, so there's the frequency. You're packing information on that frequency, and what that is saying is, so you are able to alter the signal by 100 kilohertz, which is plus or minus 0.1 megahertz. So all your information is in this window, 89.8 to 90 megahertz. Okay. So that's why the next station is 89.7 and 90.1 megahertz. Okay. So that's how come the station frequencies come about. Anyway, so here's the dipole antenna, and the energy radiated is most intense in this direction. There's no energy radiated up there. So if this were a radio station and if you were hovering in a helicopter over the radio station, you would not get any signal. All right. All right, that finishes this chapter. Oops. So that finishes the chapter, and I will ask